All right, so I want to go over error propagation briefly. Um, so in today's lab, we're going to be calculating g. And we have the equation for g. It's equal to 2 pi squared. Erase that, I made a bad parentheses. L over t squared, where L is the length and t is the period, and g is the acceleration due to the gravity. So what we want to know is we're going to have an uncertainty in our length and our period, and we want to know how that affects the uncertainty in our calculated quantity g. And so the general rule is if you have a function of one variable, now we have a function of two variables, but if you have a function of one variable, then delta f of x is just equal to the derivative of f with respect to x times delta x. So this is how much the function changes if x changes, and delta x is how much uncertainty there is in x. And so you can say that, like, if f of x is just ax, then the derivative, which I'll call f prime of x, is just a. And so delta f would be equal to a delta x. And so that's, one of the rules that's given in the manual. I just wanted to show that all of the rules that involve one variable come from that. Now, if you have two variables that are independent, it is important that they're independent. But in this case, we're measuring two things that are totally unrelated. The length and the time are completely unrelated. Then you can basically use this twice and just use the Pythagorean theorem to combine it together. They're effectively acting independently, so they're effectively different axes that are perpendicular to each other, meaning they're independent. And so you get delta f of x and y is just equal to the square root of the derivative of f with respect to x times delta x, that whole thing squared, plus derivative of f with respect to y times delta y squared. And I mean, you can move that squared around so that you're squaring delta x and the derivative separately, or you can leave it combined. So as I said, these have to be independent. If they're not independent, then you need what's called the covariance, which is how much a change in x affects y. The likeliness that you'll get a certain value of y, and vice versa. If you're measuring independent quantities, you don't need to worry about that. If you used like an intermediate calculation, so let's say that we used these to calculate something else, and then used that to calculate our final value, then that other thing that we calculated would have covariance with these. Or let's say we used g that we calculated from these two values to calculate something else, but it also had to do with these variables. Then g, the uncertainty in g would be covariant with these, because we've used them directly to calculate it. So anyway, I just wanted to point out that you do have to be careful about this. If things are covariant, there's a whole another process you need to go through where you figure out the covariance of each interrelated term. But in general, or well, usually this will suffice because you'll have independent variables. So now, if we want to apply this to the equation we'll be using today, we need to get the derivative of g with respect to x, or L. I don't know why I'm saying x. L. And if you know any calculus, since L is to the first power, that is just 2 pi squared 1 over the period squared. And then we can also say that that's equal to g over L. Now, we do the derivative of g with respect to the period. We have period is to the -2 power. So don't worry if you can't do this yourself. I'm just showing it so that you know how it's done. But if we have something to the -2 power, we leave everything else alone. We bring the -2 out. Let me put a parentheses around that. And then we subtract 1. So we get 1 over period to the third. And so this is equal to -2 g over t. So acceleration due to gravity over period. Now, if we want to, we're going to substitute these into our quadratic equation type thing that we have there. So delta, or why did I say quadratic? Pythagorean theorem type equation. It's Friday. Yeah, not quadratic. I hope I haven't been saying that the whole time. I'll go back and change that if I do. Pythagorean theorem type equation. Delta G is, okay, so we say it's square root of G over L delta L squared plus -2 G over T delta T squared. And both of these have G's, and the negative sign inside the square doesn't matter. So what we say is that this is G square root of L over delta L plus 2. Oh, yeah, ignore me. It's G delta L over L squared plus 2 delta T over T squared. And that is the equation that you will use in the lab. So I hope that makes a little bit more sense now. Again, you don't necessarily need to be able to do that yourself. I know many of you are probably taking calculus for the first time at the same time as this course. These are simple derivatives, so you know, hopefully if you have ever seen calculus at all before, you know the derivative of just x is 1, or L is, you know, if you're taking derivative with respect to L of L, it's just 1. And then for 1 over something squared, that's just a -2, so you bring out -2 power, subtract 1, get a -3 power. But yeah, and the idea here, all it comes down to is the uncertainty in something is the derivative of that thing with respect to whatever times the uncertainty in that variable. And then you use the Pythagorean theorem to combine different variables that are independent of each other. So if we had a third variable, we could just